Alrighty, in this lesson we are going to be talking about logistic models, which, surprise, it's your last AB lesson for the semester. Yay! I want you guys to think about what we did back in pre-calc in terms of logistic growth model, and we gave you this equation right here. So we have this equation, just like how we gave you the Newton's law of cooling equation back then. We gave you the logistic growth model, where we had M being your carrying capacity, K is your growth constant, and then A is your constant. Right there. We're going to extend it a little bit in terms of calculus. You'll notice that the points of inflection is when the population is growing the fastest, and this occurs whenever we have half of the carrying capacity. And that's going to be very important in terms of some of these examples that we have. The equation right here can be put into a differential equation, which is this little thing right here. I'm not going to go over or derived how we got this, but obviously you can Google how we got this or look in the textbook and see how we derived this to get this. Both of the logistic differential equations that you see are very similar, and it's essentially the same thing, whereas this one, your exponent is negative kt. This one, your exponent is negative mk times t. Honestly, it's the same thing. It just depends on if your differential equation looks like this or looks like this. So it just depends on that. So like example number 1 here, notice how your differential equation looks like this one on the left. So I'm going to copy and paste this right here so I know that it's the one on the left. We have the initial volume problem, dp dt is equal to 0.08p times 1 minus p over 1,000 with p of 0 is equal to 100. Part A says find the size of the population at times equal to 40 and times equal to 80. Well, in order to figure that out, we need the equation. And we need to figure out what M, A, and K is. Well, M is going to be my carrying capacity, and that's 1,000. So I know that I have P of T is equal to 1,000. I don't know what A is, but I do know what K is. Remember that K is my growth rate. In this case, it's going to be 0.08. 0.08. It's a 0.08. And then I know that T is going to be something. I'm going to use my additional condition now of P of 0 is equal to 100 to figure out what my A value is. Obviously, we have e to the 0. E to the 0 is 1, so I have 1 plus A. I'm going to flip-flop this. Solve for A. 1,000 over 100 is 10. So 1 plus A is equal to 10, which means that A is equal to 9. Because A is equal to 9, I have 1,000 over 1 plus 9 e to the negative 0.08 times t. All right, at this point, because we already found the equation, I'm not going to do the next step. The next step is essentially you plugging in 40 and you plugging in 80. And hopefully by now that's you doing a simple plug and chug on Desmos or on the 84. But I'm going to give you the answer so that you can check it. 731.604 and 985.266. Part B says at what time does the population reach 900? So you're going to use the equation that we found from part A and then set it equal to, plot twist, 900. I'm going to flip-flop my denominator and my 900 so that I have 1,000 over 900, which eventually turns into 10 ninths. So this becomes 10 ninths. I'm going to subtract 1, and I'm also going to make it pretty. So 10 ninths minus 1 is the same thing as 1 ninth. I'm going to divide by 9 now. That's 1 over 81. I'm going to take the ln of both sides. Then divide by 0.08 to get t being ln of 1 over 81 over negative 0.08. What is that? It's approximately 54.9306 years. All right, number 2, the solution of the differential equation dy dt is equal to 0.01y times 1 minus y over 1,000. And we want to figure out has an inflection point at what y value. It's not asking us to find the x value, it's just asking us to find the y value. And remember that the y value is when the population is growing the fastest, aka it occurs half of the carrying capacity. So in this case, my carrying capacity is 1,000, which means that my y value of the point of inflection is going to be 500. Okay, now number 3 is where things get a little bit tricky, because now we have to use the equation on the right. All right, now notice how here, this does not look like this. We have to make it look like this by, guess what? We got a factor. What are we factoring? Well, notice how p has a coefficient of 1, so we want to make sure that this has a coefficient of 1. So we are going to factor out 0.001 p, and that's going to give me p. Now, if I'm factoring out 0.001, I'm moving my decimal places 1, 2, 3 times to the right. Because I'm moving my decimal places 3 times to the right, I'm going to move 0.4 3 times to the right. So 1, 2, 3, which gives me 400. Okay, my carrying capacity is m, which we found out is 400. So m is 400. Yay. Part B says, when will the population reach 50% of the carrying capacity? Now, this problem is going to be different from number 2 because this isn't asking you about what the population is once it reached 50% of the carrying capacity. That's 200. This is saying, what's your x value of your point of inflection, essentially? So to figure that out, we have to use my equation. So we have m being 400. We have 1 plus a e to the negative m times k times t. Now we have m being 400. And then we also have k being 0.001. And if I were to do that, that's actually going to be this thing right here. So that's going to be negative 0.4 times t. All right, so to figure out what my a value is, we need to use my initial condition of p of 0 is equal to 50. So I'm going to plug in 50, and I'm going to flip-flop. Might as well flip-flop now. 400 divided by 50 is 8. Yeah, 8. So this gives us 8. We need to solve for a now. Remember that my initial condition is 0, so I'm going to plug in 0 for t, and this just wipes off. So that means that a is going to be 7. And of course, now I have to rewrite everything again. We found out that a was 7. So then your equation is 400 over 1 plus 7e to negative 0.14. And we want to see when will the population reach 50% of the carrying capacity, which is 200. Okay, I'm going to flip-flop, and I'm going to solve for t. 400 over 200 is going to be 2. Subtract 1, and then divide by 7. Take the ln of both sides, and then divide. So that's going to give me ln of 1/7 divided by 0.4. What is that? I don't know. But you could put that into the calculator. All right. Number 4, the growth rate of population P of bears in a newly established wildlife reserve is bounded by the differential equation dp dt is equal to 0.0008 p times 1 minus p over 100, where t is measured in years. Part A says, what is the carrying capacity of this wildlife reserve? Carrying capacity, 100. Surprise. All right. Part B says, what is the bear population when dp dt has a maximum value? And what does it mean in context of the problem? Remember that is going to be half of my carrying capacity, and this is when the population is growing the fastest. So, that's going to be 500. C, what is the rate of change of the population when it is growing the fastest? So we know that P is 500 when it's growing the fastest. So what I'm going to do is just plug in 500 into the equation and then call it a day. So you have dp dt is equal to 0.0008 times 500 times 1 minus 500 over 100. What is that? I don't know. Obviously, you could put that into the calculator. All right. Same thing with 5, 6, and 7. 7 is an FRQ. And then 5 and 6, I think you guys can do on your own. So essentially, these 4 problems, they're essentially the same thing, just like the growth and decay problems. Just use the formulas and then find out what your A value is. Find out your K value by, if needed, factoring. And then find your carrying capacity by, once again, factoring. All right, so after this lesson, what we are going to be doing is more review. You guys are going to have a couple 5 and 1s that are going to be for a grade, and then you'll be on your way to take the final exam. How fun!